Hi, my name is John Williams. Today we are going to be working on our bonus project. We are simulating fluid flow over a cylinder, and we are going to plot pressure coefficient points at different angles of attack. For our geometry and mesh, I am using the same geometry and mesh that we used from Project 3. I will wait till the end of this video and show you how I made all that. But for now, I just uploaded it and so we can just get right into setup. So for the first thing we're going to do is we're going to do a Reynolds number of 1 times 10 to the fifth. And we already have a problem. Okay, here we go. And start. For Reynolds number of 100,000, we're going to be using a velocity of 20 meters per second and a viscosity of 0.000245. Here's my mesh. And here we go. Okay, we are going to use standard K epsilon for our model. Okay, we're for our materials. Here we're going to switch we will maintain our density at 1.225. Looks like our viscosity is already set up for 0.000245. So we'll create that. Flows. All right, boundary conditions. We have a velocity inlet right here. Edit, we're going to edit for 20 meters per second. Right there, apply. And close, and we want to make sure our pressure outlet is a pressure outlet, and it is. We'll go to reference values here. We're going to compute from velocity inlet, 0.225. Everything here looks good. We'll surface body here. Okay, and want to make sure our methods are good. Yes, coupled, pressure second order. Okay, initialization. Let's see how we're settling here, 40. We're going to go down to 30 here. 30. Okay, initialize. It looks like everything came out okay. Run calculations, 100 iterations, and calculate. Right, calculations complete. Just get a sneak peek at our plot here. And we're looking for pressure coefficient on the wall. And here we go. You can kind of see it starts at 1. That's important. All right, let's go look at it on a chart here. We're going to close out a Fluent. Okay. And let's go to results. Got it. Okay. Expressions. All right. So my coefficient, my pressure coefficient expression, we have down here, I have pressure divided by 1/2 times the density, which we had was 1.225 times my velocity squared, which is 20 meters per second squared. Okay. And then for my theta expression, which is what I'm going to be getting my um, angle of attack on my cylinder. We're just measuring pressure coefficients along the top of the cylinder. So it should be 0 through 180 degrees. I have my negative x divided by the radius of the cylinder, which we had a radius of a diameter of 1 meter, so a radius would be 0.5. We'll apply that. So essentially, come up here to locations, go to polyline. We have, I think we already have one in here. Surface right here, cylinder surface, and this is going to be from boundary intersection. And we're going to have from wall to symmetry 1 and apply. All right, I think we're ready to start our chart. Come up here. We're going to try, let's see, pressure coefficient right here. Oh, we already have one there. We'll just call it pressure coef. Okay. Data series. We're going to go, so we have two cylinder surfaces. With a cylinder surface, our x-axis is going to be theta. That's going to be our angle of attack. And our y-axis is going to be pressure coefficient. There, and apply. And there you can see we start at 1 and we come down and over. Pretty good. I'm going to export my file. Structural mesh, files, RE3. This is not what I wanted to do. Nope. Yeah, I guess we can just do it to structured mesh files. And we are going to go with our cylinder surface here. And we want theta pressure coefficient and theta. And this is going to be RE. Okay, save. Was under structured mesh. Okay, let's go to close out here. CFD post. Now we're going to do 260,000 for a Reynolds number. So we'll go back to solution. And for our 260,000, our Reynolds number of 260,000, we're going to have a velocity of 50 meters per second. And we're going to have a viscosity of 0.000236. Okay, here we go. Again, we check our model for standard capsulon. Good there. We need to change our viscosity right here, 0.000236. Okay, change. We're staying with density at 1.225. Close boundary conditions. We're going to be so velocity of 50 meters per second. We'll change our velocity magnitude. Apply. Close. Let's see here. Pressure outlet. We're still at pressure outlet. Very good. Reference values. I'm in here at velocity inlet. 50 meters per second. Good. 1.225. Okay. And we will go to initialization, where we will initialize. Should have 30 iterations here. And we do. And we're going to calculate again. 100 iterations and calculate. All right. Calculations complete. Let's get a sneak peek of our plot here. Make sure everything came out okay. pressure coefficient, wall. And again, it looks almost like the last one, but let's go look at it in the chart. Close Fluent, okay. And we go to results. Okay, and so once again, our expression, since we just went back to solution, our expression is still for our pressure coefficient and our theta are still the same. So, and we still have our polyline set up as cylinder surface. So we can just go right into chart. We'll go with chart 7. Data series, series 1, cylinder surface, x-axis again. We have theta. And our y-axis will be pressure coefficient and apply. Oh, we forgot to change our expression. That was bad. Okay, so we're going to change the 20 meters per second to 50 meters per second. And 50 meters per second squared, we'll apply. And there we are. We're at 1 on, looks like our, right about 90 degrees at the crest of the cylinder. The velocity is at its maximum and the pressure is at its lowest. And then as the flow goes past the cylinder, the velocity comes or the pressure comes back up. Okay. And we will export this as well. RE2 cylinder surface. And need to highlight these two here. Okay, save. All right, let's move on to our next one. And now we will go back to solutions. This time we're going to be doing a Reynolds number of 850,000 or 8 times 10 to the 5th. And we will have a velocity of 12.42 meters per second and a viscosity of 1.79 times 10 to the negative 5th. So we will make sure the standard capsulon right here, materials, fluid, air, and 1.225. We'll stay that on our density. Go 0.7894 E minus 5, boom. And change create, close. We will go to boundary conditions. We're going to change our velocity here. And we will have a velocity of 12.42 meters per second. And apply, close. I just want to make sure pressure outlet stayed the same. It did. Reference values. We will go from velocity inlet. Everything here looks good. Surface body. Okay. Initialization. Initialize. All right. Run calculation. 100 iterations. Calculate. Okay, calculation complete. Now we will look at our plots again. XY plot. Pressure coefficient on the wall. And once again, starting at 1, going just below 2. Okay, file, close Fluent. Okay. Go to results. All right, we'll go to expressions. We're going to change our pressure, our velocity here in our pressure coefficient expression. 12.2 meters per second squared. Apply. Go to our chart, chart 8. And data series, cylinder surface. X-axis will again be our theta. Y-axis will be our pressure coefficient, and apply. And here we go. All right. File, export, cylinder surface. This is going to be RE number 3. Cylinder surface, and let's come up here to there we go. Okay. And let's close post. Let's go back solution for the next one. Okay, for this one, we're going to be doing a Reynolds number of 3.6 million, 3,600,000. We'll have a velocity of 52.59 meters per second. And our standard viscosity of 1.79 times 10 to the negative fifth kilograms per meter second. Okay. Model, standard K epsilon, foam fluid, air. Okay, we still have that. That's all going to stay the same. Flows, boundary conditions, velocity inlet. Let's change that to 52.586 meters per second. Apply, close. Okay. Pressure outlet's still the same. Reference values. Velocity inlet. 586, that all looks good. Initialization. Initialize. Okay. Gonna run our calculations here. 100 iterations, calculate. Okay. And let's check our plots. Plot pressure coefficient. That's the wall. And again, very similar. All right. File, Fluent. Okay. Now we will go to results. Okay, again, we're going to change our expression here. Change our velocity to 52.5 meters per second. Y. Yeah. And let's just go up here to charts. Chart 9 it is. Data series, cylinder surface, X files. Go down here to theta, Y, It's going to be pressure coefficient and apply. There it is, just like the others. All right, let me export this. Export RE4 for cylinder surface. Come up here. Save. All right, now for our final one. PFP coast. All right, and then we will go back to solution. Okay, this is in viscid flow, so we will be changing a couple things up. All right. First thing is we'll change our model to inviscid. Our materials, everything's going to stay the same there. Our boundary conditions, we're going to change our velocity inlet to 1 meter per second. 1 meter per second. Apply, close, reference values. Here we go from velocity inlet, 0.225, length 1 meter per second. Okay. Come down here to, oh wait, we have to go to methods. We're going to go to simple, and our pressure is going to be presto. Okay, now we'll go to initialization. We're going to initialize. That was quick. And run calculation. 100 iterations. Calculate. Okay, boom. All right, let's check out our inviscid plot here. Pressure coefficient, wall, and there it is. It starts at 1. Looks like it ends at 1. Close. Okay, let's close Fluent. And let's go look at a chart. Results. And okay, expressions. Change your velocity here to 1. Apply. And let's do chart 10. Data series. Gauge and cylinder surface. X-axis is theta, as always. Pressure coefficient, y, and there we have it, right there. Okay. File, export, come up here, RE5, surface, save. Okay, let's go back. Let's close this out, and I'll show you the geometry, the mesh that I created. Let's get a fresh one going here, Fluent Flow. Let's go to geometry, go over here to 2D, new design modeler. Y plane. Here we go. Let's just get right into sketching here. And we're going to start off with a rectangle. And we'll go vertical. Okay, this line, this line, this line. This is going to be 7.5 meters, 0.5 meters. And then we'll go this line, this line, and this line. And this will also be 7.5 meters. Boom. Now we'll go to horizontal. And we'll get this line, whoops, this line, and this line here. And that's going to be 16 meters. Okay, and this one here is going to be, whoops, this one and this line here. This is going to be 14 meters. Okay, now we're going to draw a cylinder. Boom. Let's come here, general. It's going to be 1 meter. There's that. Let's go up here to concept, surface from sketches. Let's go to sketch, apply, generate. And there's our basic geometry. Okay, let's go back into, oops. Oh, whoops, there we go. And let's go to mesh. All right. So first thing we're gonna do is go geometry imports. No, whoops, geometry surface body. And we're gonna change this to a fluid right here. And we're gonna generate some mesh right off the bat, see where we're at. Okay, mesh, insert, sizing. And I need to come up here. I'm gonna move this bar down here. And we will go sizing here. Y, element size, number of divisions. I'm gonna go 175 right there. And we will, let's see. Oh wait, I need this insert method. Select the face, apply. We are going to be using triangles. Boom, and generate. Okay. There we go. Insert. Let's go with some inflation here. Inflation, apply, boundary. And we'll get it on this the cylinder there. Apply. First layer thickness. We're going 0.03. Minimum layers, we're going to say 50. And 1.2 is good. Let's generate. And let's see where we're at here. Okay, now we are going to go to 0.15 for element size. And home and generate. And there's our mesh for the most part. And then we basically just name our sides here and velocity inlet. This is going to be our pressure outlet. These two sides are going to be our symmetry. And our cylinder here is going to be our wall. Okay. Then we just go back here and update our mesh. And then from there, we're ready to go right into setup and just do everything that we just did. So, all right, thank you. Have a great day.